Thermal cameras don't lie. Point one at a winter camp on the northern plains during a blizzard, and you'll see something strange. The teepee glows orange, heat signature so bright it looks like a small building. Next to it, a modern canvas tent bleeds warmth into the night like a sieve. Occupants huddled in synthetic sleeping bags, rated to -40 degrees. Inside the teepee, a family sits in buckskin clothing around a fire the size of a dinner plate. Outside, the air is -45 degrees Celsius. Inside, it's +20 degrees Celsius. That's a 65-degree difference maintained in a mobile home, made from buffalo hide and wooden poles, built by cultures who understood that winter on the Great Plains wasn't something you survived by accident. This is the teepee, not a tent, not a primitive shelter. A thermally optimized mobile dwelling that took 1,000 winters to perfect. Where every angle, every hide placement, every interior position mattered because a single design mistake meant freezing to death before morning. The Lakota, Cheyenne, Blackfoot, Crow, each refined their own version of the same solution. How do you stay warm enough to sleep when the wind hits 60 miles per hour and the temperature drops low enough to freeze exposed skin in minutes? The answer was physics, material science, and aerodynamic engineering, wrapped in a package that could be packed and moved in under an hour when the buffalo herd shifted or the weather turned. Modern anthropologists tested it. The numbers confirmed what was never in doubt. The teepee outperformed synthetic alternatives while using a fraction of the fuel. But the real test wasn't in a lab. It was every winter for generations, where failure meant death and success meant your children lived long enough to pass the knowledge forward. Chapter 1. The foundation wasn't random poles stuck in dirt. It was a philosophical statement built into geometry, and you could tell which nation put up a teepee before anyone said anything. Two systems ran the plains, each solving the same problem differently. The Cheyenne, Arapaho, and Kiowa used 3 poles, a tripod tied on the ground, then lifted as one piece. They called these the grandfather poles and set them to face the cardinal directions with real precision. 3 points made a circular floor and spread the weight evenly. The engineering held up. A tripod stays stable on its own, corrects for uneven ground, and the tension balances out once you add the other poles. This was the minimalist approach. Fewer starting poles meant faster setup and more room inside. The Lakota, Crow, and Blackfoot started with 4 poles, a square frame raised first, leaving an opening stretched toward the back. They lined these up with the 4 winds, but that 4th pole wasn't about ceremony. It was about keeping the thing from twisting. Up north, where wind didn't just blow, but hit like something solid and without warning, that 4th pole stopped the frame from torquing sideways when gusts came from different angles. You lost a bit of space, and the setup took longer, but when 70-mile-per-hour winds could show up in January while you slept, structure mattered more. Both systems worked. Neither one was a guess. These were competing schools that had spent centuries getting it right, and families drilled their kids on the sequence, the exact knots, the pole angles that kept everything standing when willows bent sidewally and snow piled hundreds of pounds onto the cover. The foundation was only half of it, though. The teepee wasn't a symmetrical cone. It leaned backward at 15 degrees, which turned it into an aerodynamic shape that made wind part of the heating system, instead of something trying to knock you over. The front face, where the door was, stood steep. The back slope ran gentler, shorter than the front by 12 to 18 inches on purpose. This wasn't about looks. It was fluid dynamics figured out through watching. When wind hit the steeper front, it went up and over, creating low pressure on the other side. That pressure difference pulled smoke up through the vent hole at the top, same Venturi effect that runs chimneys. The teepee used wind to improve its own draft. Wind on the plains usually moved west to east. The lean faced into it at the right angle, showing the smallest surface to the pressure while getting the most draw. A symmetrical cone would catch wind like a sail, building pressure inside that could rip the cover off the stakes or fold the frame inward. The lean made the structure slip past wind instead of fighting it. At ground level, the cover's bottom edge got staked tight or held down with river stones, an air seal. But small gaps were left on purpose on the downwind side, controlled intake points that fed the fire oxygen without creating drafts where people slept. The whole thing worked together. Wind direction set where you put the stakes, which set where the intake gaps went, which fed the fire, which made heat that rose and left through smoke flaps you'd already adjusted for that same wind. Winter storms didn't fight the tipi. They made it run better. Stronger wind meant stronger draft, which meant cleaner burning, which meant more heat from less wood. The structure turned the thing that killed people into the thing that kept them alive. Chapter 2. The two fabric triangles at the tipi's crown weren't decoration. They were adjustable vent panels, smoke flaps you could control from outside in seconds without stepping into a blizzard. Each flap had an external pole that slid into a pocket sewn along its edge. You repositioned these poles from the ground, changing the vent opening for whatever the wind was doing. Calm air? Both flaps spread wide in a V, letting smoke pour out. Steady wind from one direction. Close the upwind flap, open the downwind side. Pressure difference pulls smoke straight up like a chimney. Swirling wind? Angle both flaps inward to form a narrow slot that stops backdraft but still vents gases. Heavy snow or freezing rain? Overlap the flaps to make a weather shield. Leave just enough gap for smoke. Extreme cold? Nearly closed, accepting some smokiness inside to keep heat from escaping. The person tending the fire, usually women or elders who held this knowledge, developed a feel for it. They read smoke the way a pilot reads instruments, adjusting in real time as wind shifted or temperature dropped. The flaps weren't something you set once. You worked them all day and night as conditions changed. At the apex where the flaps met, two more sticks crossed through reinforced holes in the hide. You could adjust these from inside with a long pole, fine-tuning without going outside. When a January blizzard hit at midnight and the wind reversed, someone could reach up from their sleeping robes and reposition those crossing sticks to stop smoke from pouring back down into the living space. Adjustments took seconds. Effects were immediate. Get it wrong and you're looking at carbon monoxide poisoning or heat loss so fast, the internal temperature drops to dangerous levels within an hour. Smoke management didn't stop at the exit point though. The fire itself was positioned as part of the system. The fire pit wasn't centered. It was offset 2 to 3 feet toward the door, creating a longer path for smoke to travel before reaching the exit hole at the peak. That extra travel time meant more heat transferred into the living space before the gases escaped. The pit was dug 6 to 8 inches deep and lined with flat river stones, specific rocks that absorbed heat without cracking from thermal shock. During active burning, these stones charged up with thermal energy. After flames died to coals, they radiated stored warmth for hours. Thermal batteries that kept the interior warm through the night. Hot smoke rose from the forward-positioned fire, hit the peak, then traveled backward along the underside of the cover and the inner liner before exiting. The hottest air in the structure passed directly across the sleeping area at the back, transferring heat to the space where people spent winter nights. Every foot of smoke travel meant more BTUs delivered to occupants instead of lost outside. Old ash stayed in the pit bottom on purpose. It insulated the ground underneath, stopping heat from conducting down into frozen earth. The ash layer kept pit temperature up between fires, so you needed less fuel to bring the next fire up to effective output. The fire itself was small, fist-sized pieces of dry cottonwood or willow, not the massive log fires modern people picture for winter heating. Small fires burned hotter and cleaner, producing less smoke while generating enough heat in an insulated space. A teepee fire used 8 to 12 pounds of wood per day. A modern canvas tent trying to maintain the same temperature differential needed double that because its smoke management was primitive and it had no real insulation. The flaps and the fire worked together. Adjust the flaps, you change the draft. Change the draft, you change combustion efficiency. Change combustion efficiency, you change heat output. Reposition coals in the pit, you alter where radiant heat goes. Move stones from pit edge to pit center, you change thermal mass distribution. Chapter 3. A teepee cover wasn't something you bought. You built it from scratch over months, turning raw buffalo hides into weatherproof architecture through 15 steps that sound more like industrial chemistry than craft. Fresh hide came off the animal weighing 70 to 90 pounds, covered in fat, blood vessels, and a membrane layer that would rot within 2 days if left attached. Women staked it hair down on the ground and began fleshing. Using scrapers made from elk horn or sharpened bone, they removed every trace of tissue, working in systematic strokes that cleaned the hide without puncturing it. The thin membrane between skin and flesh had to come off completely. If it stayed, bacterial decomposition would start there and spread, a stinking, unusable skin within days. Then came brain tanning, the chemical transformation that turned stiff rawhide into supple leather. Buffalo brains were mashed into paste, mixed with water, and worked into every inch of the hide. The lipids in brain tissue broke down collagen structures in the skin, softening fibers and making the material pliable. Every animal has enough brains to tan its own hide. Wasn't folk wisdom. It was biochemical accuracy. One buffalo brain contained exactly the enzymes needed to process one hide. The hide was stretched repeatedly while damp, pulled and twisted and worked until the brain solution penetrated completely and fiber bonds broke. This took days. Arms got tired, hands cramped. You couldn't stop because if the hide dried before the process finished, it would lock into stiff rawhide and the entire effort was wasted. Smoking came last, the step that separated functional leather from weather-resistant shelter material. Multiple processed hides were sewn into a cone shape and suspended over a smoldering fire of punky willow or cottonwood. Not flames, smoke. The cone trapped dense smoke that deposited creosote and tar compounds deep into hide fibers. This did 3 things. Made the hide water-resistant, so rain beaded and rolled off instead of soaking through. Prevented the leather from reverting to rawhide when wet. And added preservation that blocked rot and insect damage for years. The color change was visible. Pale cream transformed to golden brown. The functional change was molecular. Modern chrome tanning uses different chemicals to reach the same goal: permanent transformation of collagen structure. Brain tanning and smoking arrived at the same destination through observation and refinement instead of laboratory analysis. A single teepee needed 12 to 20 hides depending on size. That meant 400 to 600 hours of skilled labor: scraping, tanning, stretching, smoking. Then came pattern cutting, layout planning, and final assembly. Hides varied in size and shape, so no 2 teepee covers were identical. Women developed spatial reasoning that let them visualize how irregular hides would fit into a precise semicircular pattern that, when wrapped around a conical frame, would meet with minimal gaps. Sewing used sinew thread made from buffalo or deerback tendons. Sinew had a property that synthetic thread can't match. When wet, it swelled to fill stitch holes and created nearly waterproof seams. The seams themselves were reinforced at stress points, around smoke flap pockets where wind load concentrated, at stake loops that held the cover to the ground, at door edges that opened and closed daily. These areas got double or triple thickness. Winter covers sometimes used hair-on hides for the innermost layer, creating an additional fur barrier that trapped air against the hide surface. Some tribes used double cover systems in deep winter, an old cover inside, a new cover outside, with an air gap between them that worked as insulation cavity. The gap was only 3 to 4 inches, but dead air is one of nature's best insulators. The finished cover weighed 90 to 120 pounds and was a family's most valuable possession after their horses. It could last 10 years with proper maintenance, patches, re-smoking, repairs to worn areas. Modern canvas tents rot within 2 seasons of hard use and provide a fraction of the weather resistance. Converting buffalo into housing required technical knowledge as sophisticated as any modern material science. The difference was that women held this expertise and passed it daughter to daughter through hands-on teaching that modern engineers would recognize as apprenticeship. These weren't people using what nature provided. They were chemists and engineers working with organic materials, applying principles that remain valid when tested in contemporary labs. Chapter 4. The liner hanging from shoulder height around the tipi's interior was what made the difference between barely surviving winter and actually living through it. People see the painted hides, family stories, geometric designs, and think decoration. They're looking at the most important thermal component in the whole structure. It stood 5 to 6 feet tall, hung from thin poles tucked between the main frame and outer cover. Ran the full circle except at the door. Between the liner and the outer hide sat 4 to 6 inches of empty space. That gap did the work. Dead air trapped between 2 surfaces doesn't move. It just sits there, insulating. Same reason double-pane windows work, or why down jackets keep you warm. Air caught in the fibers has nowhere to go. The liner created a stationary air pocket that blocked heat from escaping through the outer wall. Without it, a teepee loses heat twice as fast. That gap alone handled 40 to 60% of the shelter's thermal efficiency. It also solved condensation. 6 people breathing in a sealed space all night produce gallons of moisture. In sub-zero cold, that vapor hits the coldest surface and freezes. Without a liner, that surface would be the inner wall of the hide cover, right above where people slept. You'd wake up to ice forming overhead, then melting from the fire's heat and dripping onto your face. The liner stayed warmer than the outer cover because it faced the fire. So moisture condensed on the outer hide instead, behind the liner where nobody noticed. It ran down into the gap and soaked into the ground at the teepee's edge. People stayed dry. The system didn't fight physics, it just rerouted it. Ground drafts, the kind that make sleeping miserable, hit the liner and stopped. Wind leaking through seams in the outer cover couldn't reach the living space. Inside the liner, the air stayed still even when storms tore across the plains outside. And because the liner was pale or painted light colors, it bounced radiant heat from the fire back into the room instead of absorbing it. Dark hides would have swallowed that heat. Chapter 5. The teepee kept families alive at minus 45 degrees Celsius, but that's only half of what made it work. It could also be packed and moved in under an hour. On the plains, that wasn't convenience. It was survival. Disassembly started inside. The liner came down first, untied from its poles and rolled, not folded. Bedding got bundled, sacred objects secured. Parfleches, rawhide containers for tools and personal items, went into their usual order. 15 minutes and the interior was cargo. The cover came off next. They unpinned it from the ground stakes and unlaced it while the frame still stood, so the hide didn't drag through dirt. 2 people could drop a teepee cover in 10 minutes. folding it in ways that kept the smoked leather from getting permanent creases. Then the frame. They released the foundation poles, and the whole structure fell in a controlled drop, heavier poles guiding which way it went. 5 minutes from standing to bundled. Loading the travois took the most time. The poles became the travois, 2 long pieces forming an A-frame that dragged behind a horse, with a platform lashed between them. The cover, liner, and belongings got strapped to that. A family needed 2 or 3 horses, 1 for the teepee itself, 1 or 2 for everything else. Setup was the same process in reverse, a little faster if you'd done it before. 45 to 50 minutes from bare ground to shelter, that worked. That mattered, because conditions on the plains moved faster than permanent buildings could handle. Blizzards showed up with 30 minutes of warning. Buffalo herds shifted without pattern, and if you wanted meat, you moved when they did. During conflict, staying in one place too long meant getting trapped. Plains tribes moved 12 to 20 times a year, tracking game and weather in ways a fixed structure couldn't. Agricultural tribes, Mandan, Hidatsa, Pawnee, used earth lodges that held heat beautifully, but couldn't go anywhere. When winter game left, or enemies closed in, that immobility killed people. Mobile tribes could move toward better conditions. 50 miles east might be 10 degrees warmer with a ridge blocking the wind. The teepee made that possible. Home wasn't a place. It was a system that went with you, keeping full winter protection no matter where survival pulled you next.